Welcome to Seeking Delphi, Episode 14, Replicating Machines. I'm Mark Sackler. The future lives here. Researchers at Carleton University in Ottawa, Canada, recently announced they are developing an extraordinary device. It's a 3D printer that can make copies of itself. Where and why would you want a machine that can do that? In 3 easy words, on the moon. It is difficult and expensive to launch equipment into space. A device that could use materials in situ to build copies of itself, as well as the needed equipment, would make manning and mining the moon, Mars, and asteroids orders of magnitude easier. They might, in fact, be the only practical solution. But just how hard is this to accomplish, and could such machines be controlled once let loose? In his 2013 novel, Creations, science fiction author Will Mitchell explores these questions while adding an additional one. What happens if they evolve? I recently put in a call to Will at his home in the south of England to get his comments on these issues. Will, thank you for joining me. Welcome to Seeking Delphi.
Thank you very much, Mark. Thanks for the invitation to come on.
To begin with, Will, tell us a little bit about who you are and what brought you to write Creations.
Well, I live in the south of England and I work in my day job in aerospace research, which at the moment involves jobs like developing the software for flight simulators. And I also run research projects looking at emerging technologies in radars and airborne communications. In the past, I've been involved in jobs like airframe design and aerodynamic performance prediction, including what back then were quite unorthodox design methods such as genetic algorithms and simulated evolution. And at one point I was also involved in machine learning and AI, looking into how well suited they were to aircraft control systems and autopilots. In my spare time though, I'm a writer, initially a published writer in the horror genre, but more recently I've moved over to science fiction. Writing's currently a hobby, but one which hopefully benefits from the fact I deal with these kind of technologies on a day-to-day basis. Especially as the kind of writing I do nowadays is mainly hard SF, hard science fiction. So that is science fiction with a strong emphasis on technical plausibility. As far as Creations is concerned, that's the first full-length novel that I've written and had published. And the idea for that came to me actually a long, long time ago when I was reading the novel 2010 by Arthur C. Clarke. And I think I was in my early teens at the time, so we're talking a long way back in the past. But at one point in Clarke's novel, the black monolith around Jupiter is compared to a von Neumann machine or a self-replicating machine. And at that point, I'd never even heard of the idea or even considered it as a possibility, but just that reference all on its own was enough to get me wondering, could you actually build a machine that could copy itself? What would you get if you made one and set it running, say, on the moon? And all these ideas started coming out about, like the idea of a vast automated city populated only by robots, growing and spreading over time and possibly even evolving or redesigning itself as it went. And I wondered, what would that look like if you came back a year later or 10 years later? The thing would be absolutely vast by then and probably wouldn't look anything like the machine you'd first started with. It'd almost be like a kind of alien life, but something that you'd created yourself, made of metal and silicon instead of organic matter. And I thought the idea was absolutely fascinating, especially given that everything I read on the subject suggested it was entirely plausible. So when I took up writing, this seemed an obvious subject to cover. The next thing I wondered was, what if it went wrong? What if the thing you'd created became actively hostile to humankind, or to anyone or anything that went near it? And if it was designed to do a useful job like mining or manufacturing, what if something like natural selection took over, so the machines which were best at surviving and reproducing, not necessarily the ones most useful to us, were the ones that went on to create the next generation? Would the result count as a kind of artificial life? And what would that mean for us if the thing we'd created ended up being stronger and faster than us? So once I began thinking along those lines, the rest of the story just fell into place pretty quickly. It just took a lot longer than it should have done to write it and finally get it published.
In the book, there is a reference to these replicators as effectively being alive. But how would you distinguish between a biological replicator and a machine replicator, or is there any difference?
I think there are a lot of deep running parallels between biological life and what we would probably have to call machine life if we were to create it. I mean, the idea of self-replicating machines has been around for a very long time. First person to look at this seriously was a guy called John von Neumann, who I'm sure you and most of your listeners will have heard of, but he was one of the greatest minds of the 20th century. And he came up with this theory of automata that he developed, starting back in the 1940s. And he was looking at the whole thing from a mathematical perspective. First of all, to confirm that the idea of replicating machines was even possible, but secondly, to try and figure out what capabilities and functions a replicating machine would need in order to be able to duplicate itself. And that first question, the basic feasibility of the whole thing, that's the one you have to get out of the way right at the start, because if you look at this issue wrongly, you can come to the conclusion wrongly, but it's not possible at all. So the first hurdle you have to overcome, the first major fallacy we need to get out of the way, is the idea that a machine, something that we would think of as being like a robotic machine or a production facility, it can only make something simpler than itself. And it's a very easy fallacy to fall into. If you think of a production line making cars, no matter how many cars you pump out, there's no way those cars could team together and build another production line. Very easy trap to fall into and wrongly see this as a fundamental block. But von Neumann, via his mathematical treatment that he gave the subject, proved that machine replication was in fact possible. And one of the things that confirmed it for him was this deep similarity between machine life and biological life, because he realized that all life forms, anything from bacteria upwards, they really are a kind of machine, albeit working by chemistry rather than robotics. So that parallel between machine replication and biological life is central to the whole thing. Because another major fallacy that you have to get out of the way is the idea that only biological systems can duplicate themselves. It's easy to fall into that trap as well, of thinking that biological matter has a kind of life force associated with it, as if replication or self-duplication is some kind of mystical process, but really it isn't. It just follows the laws of physics. So if you imagine something very simple like a bacterium reproducing, it takes in raw materials from its local environment. It then performs various functions on those raw materials. It reorganizes them and recombines them according to plans coded in its DNA. What you get at the end is a copy of the original, including its own DNA blueprint, which was crucially copied from the first bacterium, which allows it to then make further copies. Well, when von Neumann tried to figure out the basic plan for a replicating machine, he realized the exact same kind of functions would be needed. You'd need a machine that can take in raw materials, process them or arrange them using some kind of fabricator, and the whole thing would be run according to an instruction set on a tape or a disk or whatever data medium you choose. Then when the machine has copied itself, the final crucial step is to copy those plans over to duplicate the data file, like a kind of software transfer coming alongside the hardware. And mathematically, he was able to prove that something built like that is not only capable of reproducing, but it's directly analogous to how biological systems reproduce. Whether it's made of organic matter or metal and plastic doesn't matter, whether it uses DNA or data files, as long as it has the functions and components that he identified as being necessary.
Will, researchers at Carleton University in Canada recently announced that they are working on a 3D printer that will be able to replicate itself. The idea being to use materials in situ on the moon, Mars, asteroids, whatever, in order to help facilitate exploration and perhaps ultimately mining on these bodies. Talk about the importance of this.
Yeah, the potential use of this kind of technology in space exploration, this is really where it will come into its own, because as we all know, Earth's resources are finite, the amount of power we can generate is finite, but elsewhere in the solar system, the resources available there in terms of precious materials and metal ores and all the other useful stuff you'd want to go out and accumulate, it is whole orders of magnitude more than we have here on Earth. However, there is a big problem to developing that kind of non-terrestrial industrial capability, and that is Earth's gravity well. We live at the bottom of a very deep gravity well, and pushing things up that well is very, very expensive. That first 100 miles straight up is phenomenally difficult and expensive to cross. Once you're up there, though, things are a lot easier. Landing on the moon and taking off again involves a fraction of the fuel that it took to get there from Earth. The same is true of Mars, and it's especially true of the asteroids, where you're pretty much working in near zero gravity the whole time. However, the Moon, Mars, and the asteroids, those are all very hazardous locations. So ideally, you would want to automate any industrial capacity that you produce as much as possible. So it's starting to look like the best way forward, if you want to establish a wider, more permanent presence in space without having to ferry every bit of equipment and fuel from Earth, is to develop something self-sustaining, something which can use local resources without needing hardware or material to be supplied from Earth. And in fact, a year or so ago, the White House Office of Science and Technology Policy started looking for ideas on how something that they termed massless space exploration can be performed. And the aim is to find the smallest amount of hardware which can be launched into space, which can then kind of unpack itself to form a self-sustaining mining and manufacturing infrastructure. And autonomous self-replicating machines show a lot of promise in that regard. And if we wind the clock back 37 years to 1980, that's when NASA started to look at this very seriously. They did a big engineering study. And basically, from June to August of that year, they spent 2 months coming up with concepts for self-replicating lunar factories intended to strip mine the surface of the moon with an ever-increasing population of automated fabricators, starting from a single robotic seed. What they did was to go beyond the mathematical proof of concept that John von Neumann had carried out and start to look at this as an engineering problem. So how, at the nuts and bolts and computer chip level, could you actually make a replicator? And what we found was the complexity of a self-replicating system depends on what raw materials you give it. And there are a couple of thought experiments they went through that put what's involved into perspective. So basically, the simplest self-replicating machine you can think of would be like a robot arm that can pick things up and move them around. You give it its raw materials in two forms. The first one is another identical robot arm, complete in every detail except the battery that plugs into the side is missing. Raw material number two is the battery. The machine picks up the battery, plugs it in, and all of a sudden you've got a copy which can go on to make other copies. Now that's a highly trivialized example because it only has to perform one function on raw materials which are highly organized compared to the finished product you want to end up with. But what they realized is the best way to approach this problem is to take an incremental approach. So make the raw materials less and less organized bit by bit. So you can have another thought experiment with a robot that's roaming around a storeroom surrounded by racks of spare parts. It needs to be able to identify the parts and plug them together and make electrical connections and those kind of things. And if you can get that to replicate, then you take it to the next stage where you give the thing just sheet metals and lengths of wire and so on. So then it has to start welding and cutting and joining metal together in order to copy itself. And that's when you start to see the complexity ramping up, because if a thing needs to weld metals and bolt things together, whatever tools it uses to do that, it needs to be capable of making those tools whenever it duplicates itself as well. So you start to get a kind of an increase in complexity. But you take this thought experiment further and further. Next, you just give the thing metal ores, where it needs some kind of chemical processing plant to extract the metals so that it can make the sheet metal and all those things, which it then has to weld together. And the ultimate extreme is you don't give it anything. It has to move around and find its own raw materials. And that's the kind of thing you would need to do in a lunar environment or up in the asteroids. And that's the kind of the end state for something that can autonomously self-replicate. The increase in complexity from one end of that spectrum to the other end is absolutely phenomenal. But at no point do you ever hit a fundamental problem. And they were able to prove that this kind of thing could be done. And if you do that, then you end up with something that can replicate endlessly without any external support or assistance. But there's one big issue they found, and it's something they term closure. And basically, closure is a central issue in all self-replicating systems. If you list all the parts a machine is made of, and then on a second list you put all the things it's capable of making, if this thing's going to replicate itself, everything on that first list has to be on the second list without exception. It has to be able to make everything it's made from. And closure is expressed as a percentage. 100% closure means the thing can replicate. 99.999% isn't good enough. Because if there's even one component the thing depends on but is unable to make, that's enough to stop the whole thing. And the NASA researchers, they even had to consider what would happen if 100% closure wasn't possible. And a good example is high-grade integrated circuits or processor chips. You need complex clean room facilities to make those for growing single crystal silicon wafers. And if that kind of chip making facility is included in the replicator design, the factory has to be able to make that chip factory as well as just the chips themselves. And if making that chip factory needs additional unique capabilities, they not only have to be included in the design, but the system needs to be able to make those things as well. So you quickly end up with a design spiraling out of control. You need component A just to function, but to make component A needs components B, C, and D. To make B, C, and D needs D, E, F, H, and so on, and ad infinitum. And they realized reluctantly, I think, that you might find in a realistic replicator, some tiny proportion of the parts can't actually be made themselves and need to be supplied from Earth. And they refer to these as vitamin parts. But obviously, you want to minimize that. You want to work as close to 100% closure as you can get. And if you do achieve it, then you have something that really can replicate with no external assistance.
Well, in the book, things accelerate out of control, not just because the machines can replicate themselves, but because they can evolve at an accelerated pace. Using computers to simulate evolution in design is something that's been going on for quite a while. And here in the book, the combination of the two turns out to be quite powerful. Tell us about that.
Well, in my day job, I've used simulated evolution as a design tool before. And that's a career path that I gave my main character, Max, in the novel, not only to make him invaluable to the project that's depicted in the book, but also to let him be the one who appreciates how powerful evolution can be as a design tool. And he's the one who warns everyone else that what they're letting loose might not be as easy to control as they're assuming, and ultimately he's proved right. But when I've done this kind of work myself in the past, it's been for jobs like designing wing shapes for aircraft, where you sort of have a population of thousands of candidate wing types, which are developed at random to begin with. But then you test them all in aerodynamic prediction codes. And the ones that have the faintest glimmerings of decent performance, you take those, discard the others, use them as a basis for the next generation. And you just do that time and time again. And you end up with something that works very, very well. In fact, in many cases, it works better than anything a human designer could have come up with. In Creations, my main character, Max, he's called on to help design these machines because it's understood that his skills are the only way that something that complex can be designed. But once those machines are designed and let loose, the intention is that they will keep their design fixed and won't change, or that's the aim at least. However, later on in the book, I don't want to give too much away here, but replicating machines are developed which deliberately modify their own design from one generation to the next in order to maximize their ability to harvest the kind of materials and resources that they've gone out to get. And that's actually something that NASA research team back in 1980, they actually considered this, that you could make each machine think or run simulations or make decisions about how its job would have been easier if some of its design features were different, and build those modified design features into any machines that it makes. So you get something which is kind of like evolution but sped up, and it's driven in a way that evolution isn't. Genuine natural selection is obviously very, very random, although the filtering process that lets some entities survive and some die is not random. But if you've got something which can, I won't say consciously, but something that can deliberately modify its own design and put those changes into the machines that it makes, you get something which is going to modify itself very, very rapidly in a very short time. And there are some very exciting possibilities from that, because you'll get something which is like a form of artificial life, which can modify itself and spread much quicker than anything you could design. But there's also some scary implications to that as well, because if you think you're going to keep full control over these things, then you're probably going to be mistaken. Now, of course, if someone like NASA did this, if they did a whole NASA-style replicator program, they would design the thing from the outset to remain under the control of the people who set it running. However, Creations obviously is fiction, and in fiction you need jeopardy, or in this case outright carnage, so some things have to go wrong. So for plot-related purposes in Creations, the machine's designers are grossly negligent in how they oversee the machines. In reality, though, I'm looking forward to seeing these kind of replicating machines built, because I think they will fulfill all the promises people make about them. And as far as this technology is concerned, as long as it's done sensibly, then I'm an optimist rather than a pessimist. But it is actually quite possible to go either end of a spectrum of optimism or pessimism when looking at this technology. If you're on the optimist side, you could see this as a new industrial age. You can think we've gone through the Stone Age, the Bronze Age, Industrial Age, the Information Age, and then the replicating age will be a new age of humanity in its own right. We'll have these machines as tools helping us to do things on a previously unimaginable scale. And the kind of things that people have put forwards are you could do strip mine the entire surface of the moon in a matter of decades and take all of those resources. You could have machines that can take infinitely large amounts of matter and turn it into self-organizing systems. You could make exploration machines. You could have replicating space probes but go out through the solar system and beyond. People have seriously considered this for the interstellar domain, where you have this wave of exploring machines copying themselves and multiplying at an exponential rate, but they're all beaming their findings back to Earth. You could do materials retrieval from elsewhere in the outer solar system. In fact, one of the ideas that was first put forwards was to go to the moon of Saturn, Enceladus, which at that time was known to have an icy shell to it, and to take lumps of ice from there and using a mass driver to throw them back towards Mars as a terraforming exercise. So when they break up in the atmosphere of Mars, they add to the water content. And if you have replicating machines performing this job, then you'd have enormous amounts of water being delivered to Mars automatically, completely autonomously, and terraform the whole planet. In fact, most terraforming schemes you can think of could be aided by self-replicating machines that would make the whole thing go much, much faster. You could do stellar-scale mega engineering projects, things like Dyson spheres. Everyone's been reading about Dyson spheres lately because of the Tabby's star and the lingering mystery about what's blocking the light around that star. Is it some kind of alien megastructure? Well, if you wanted to build something like that using the constituent matter of a whole solar system, replicating machines would be the way to do it. And these things that sound completely outlandish just due to the sheer scale of them, but if you have something that grows exponentially, those concerns are no longer valid. Something that would be unthinkable as a purely human endeavour suddenly becomes feasible when you're aided by replicating machines and exponential growth. And the NASA researchers who looked into this back in 1980, they saw this as a new industrial age. It was even referred to in their report at one point as the last machine we ever need to build. And they talked a lot about the social and economic implications of building this thing, population control among the machines, how to pull the plug if you need to, the likelihood that a self-replicating system, given a high degree of autonomy, will be able to circumvent any controls that we put on it. And that obviously came in very useful for my work on the fictional side of this. But the NASA researchers, they also went into the philosophical and ethical and religious questions about this, about effectively creating a new form of life. Are we going to have effectively robot slaves? Do we need to think about machine rights? Or what would, if a robot's developed intelligence, how would they then see us? And it's actually fascinating to read this stuff because fundamentally this is a NASA technical report. It's an engineering report. You normally read these things, you're seeing valve designs and fuel flow rates and orbital mechanics, but here they're talking about the philosophy of creating artificial life. And it's a natural extension of where they started with that initial feasibility study. You can't really avoid those kind of questions, so it's good to see them going down that path. But that's the optimistic side. As I said, there is a pessimistic side as well. You could view that self-replicating machines, particularly if we lose control of them, as being a self-imposed extinction-level event. And that, in many ways, that's also an equally valid way of looking at it. And it certainly informs the design choices you would have to make and how you controlled these machines and how we would exist alongside them when they outnumbered us by several orders of magnitude and managed to reach through the solar system and beyond, doing the jobs that we want them to do. So there's a lot of ethical issues surrounding this as well. But I put myself on the techno-optimist side of this rather than techno-pessimist. Although in the book all hell breaks loose and it seems about a carnage, in reality I would like to see someone build these things.
One final question, Will, and that's to do with timeline. In the book, you set 2040 as the year where all this happens, including exploitation, mining of the moon using replicators. It's been 4 years since you've written the book. How do you feel about that timeline now based on what you've seen so far in the subsequent time?
Things have come on a long way since the NASA study. The self-replicating lunar facility that the NASA researchers came up with didn't involve 3D printing explicitly. It was more like a warehouse and a production plant. It was more built along the way that automated production lines are built. So it had a chemical refinery, it had a parts depot, it had a fabrication sector and a parts storage sector and all those kind of things. It's laid out the way a car plant would be effectively. And some of the production methods they looked at things like vapor deposition for creating some components. They looked at powder metallurgy as well. And those things, we see them mentioned when we talk about additive manufacturing as we currently know it. But the NASA researchers didn't explicitly think 3D printing was one of the things they need to do. And this issue I talked about before of closure, you want to have a single manufacturing process that can make the widest variety of parts and types of mechanisms, because that really helps with your closure problem. And a 3D printer or additive manufacturing, maybe putting down layers of powder and sintering them with concentrated sunlight or something like that, that seems like a very viable way of doing this. So that kind of basic research onto the functionality and methods you would need to make this real, that has been very, very promising. I think there are still some big hurdles to cross. I think it's going to be a long time until someone unpacks some 100-ton robotic seed on the moon and lets it reproduce endlessly without any external assistance required. But there's a lot of people working towards this right now. There's a lot of people working in the right direction to do this. The researchers at Carleton University in Ottawa, what they're doing with the electric motor designs that they're proposing is a step in exactly the right direction. The kind of 3D printing they're talking about isn't just the sort of fast prototyping that we saw when 3D printing first came onto the market a couple of decades ago. You're looking at something that can lay down entire mechanisms, so putting different materials down, some of which are conductive, some of which are insulating, some are structural, some are magnetic. But if you lay them down layer by layer, then in a single pass you get a complete mechanism with moving parts and electrical components and magnetic components. And what those researchers in Ottawa are proposing is to try and 3D print an electric motor this way, because that's something that's never been done before, and it has all those different features within it. And if they can print that thing in a single pass and show the thing works, that's a big step forwards. So the fundamental research which is going to feed into this kind of replicating technology is definitely going in the right direction. It's definitely going a lot faster than I'd anticipated. But for the end state, to actually get replicators done, it's possible that I was being optimistic with the 2040 year, but who knows? It may come along and surprise me.
Will, thank you for joining me, and best wishes for your future endeavors in both writing and engineering.
Thank you very much, Mark. I really enjoyed our talk, so thank you again for the invite.
Creations provides a chillingly plausible scenario of machine automation running amok and out of control. Will Mitchell's engineering background is evident throughout the book as he deals with the technical issues, what goes wrong and what goes right. But Creations is also a page-turner and a worthwhile read, whatever ultimately happens with self-replicating machines. In the news, apropos to this program's subject, the Japanese space agency JAXA recently announced plans to send a man to the moon by 2030. This upstages China's previously revealed plan to reach the lunar surface with a manned mission in 2036. It possibly sets the stage for an Asian space race. Move over Elon Musk. His tunnel-digging operation, dubbed the Boring Company, appears to be getting some competition from Europe. The EU is sponsoring a venture to create a tunneling robot called Badger, or Robot for Autonomous Underground Trenchless Operations. It will be able to maneuver, dig, and navigate underground. However, its use will largely be in construction and not transportation. Speaking of Elon Musk, Tesla has begun producing its mass-market Model 3 electric vehicle. The aim is to ramp production up to 20,000 cars per month by the end of 2017. And finally, again on the subject of automation, the Emirate of Dubai has made it known that despite its rollout of robot policemen, it does not intend to replace its human cops. I think the world's donut shop owners just heaved a collective sigh of relief. My thanks to Will Mitchell for today's interview and to you for joining me. You can subscribe to these podcasts on iTunes, Player FM, or YouTube, and follow us on Facebook. As always, your comments, questions, and suggestions for future content are always welcome. Until next time, I'm Mark Sackler.